Hi everybody. This is the math course, the operations on the real numbers course. I'm Mr. Nazelli and I'm really excited to kick off the course with you today. So let's get right to it. The first thing I want to do is I want to welcome you to the course. I think you're going to find this really informative and hopefully a lot of fun. Before we get into the mathematics, I just want to share with you some expectations that we have about how you should interact and engage with and around these videos. The first thing I want you to know is we want you to be ready when you're watching these videos. We want you to be active. And to us, that means we want you to have your notebook open, your pencil in hand, and that way you can take notes. You can jot down anything that you think is important, any questions you have, and you can get them answered afterwards, or maybe they get answered later in the video. But taking good notes is a really good skill that's going to stay with you through college. This is the math core. So you know we're going to push you to overcome your fears. And in these courses, the main fear that most people have is the fear of being wrong, of saying something that's incorrect. I know that's difficult, but I also know that we learn best by making mistakes. So don't be afraid to stretch yourself. Try something out of your comfort zone. You should know that everybody in the math core is going to be there to support you. Now, during discussions that you have about these videos or within these videos, I think you want to follow the standard protocols as you do in a live class. That is, if you want to say something, you should raise your hand just to make sure that goes smoothly. And in fact, the use of signals, the math core signals, is probably even more important in this virtual environment. So if you want to agree with something that someone's saying, you can show them that with this signal. If you disagree with something that's been said or written, you can disagree. And then, of course, if someone is trying something difficult or getting stuck somewhere, you can show them support as we go. All right, let's get right to the mathematics. This is a course in the operations on the real numbers. Before we can talk about the operations on the real numbers, I guess it's really important that we understand the real numbers. So let's make that our first order of business. What are the real numbers? Well, a nice easy way to think of them is as all the integers along with the numbers in between them. Okay, so the real numbers are all the numbers on the number line, and you've got your integers and the numbers in between. All right. I feel like we keep going backwards, but here's one more step. Let's make sure we know what the integers are. So the integers on the number line, they are made up of the whole numbers, which you see here, 0, 1, 2, 3, 4, those guys, together with their opposites, the negatives on the left side of 0. So in some sense, we can call them the negative whole numbers. It's not totally right, but I think that gets the point across. You've got the whole numbers, 0, 1, 2, 3, 4, etc., and then their opposites, these negative whole numbers. Okay? Well, for a moment, before we get to the integers, let's make sure we just have that right side covered, the whole numbers. Okay, we'll look at those for a moment. There are an infinite number of those. Even though my number line stops at 8, you know that they just keep on going. So there are an infinite number of whole numbers. And it turns out you don't need to know a million things about them. There's really 5 key ideas that you got to have when you're dealing with the whole numbers. Number 1 is you need to be able to read and write them. Okay. Number 2, you need to be able to count with them. Now, counting with them, I think you're probably pretty good at that. You just have to watch the turns. Like you need to know that when you have 999, the next number in that count is 1,000. So you have to pay attention to when you're sort of changing big groups. We'll talk about that a little bit in a second. You also need to understand the individual decimal places. The system is really super packed and really cool. So every position means something different. Okay, that's really important to know too. You also need to know how to approximate whole numbers just have a number sense. So if you walk into a store and you see something advertised for like $698, then you got to know that that's like $700. No big deal, okay? The last thing is you have to be able to operate on the whole numbers, add, subtract, multiply, and divide them. Again, I've got a feeling that that's going to be pretty good. If not, you're going to have plenty of opportunities to strengthen all of those skills. I just want to talk to you about the first one really quickly, because to read and write, remember, these whole numbers go on forever, so they can get really big. So like, for example, if you had this monstrous number, it looks really intimidating, but to read it and to write it, you really only need to be able to handle 3 digits at a time. See how they're kind of grouped in 3 digits? Well, that's on purpose because the little commas separate really important groups. So for example, we've got number, comma, number, digit, comma, etc. Okay, and that's going to go on as far as you want to go. And those commas, like I said, they mark off important divisions in these different groups of 3. So that middle group, that's where the thousands are. And then to the left of that, that's where the millions are. So if you want to read a big number like this, you just read it left to right, and then read the 3-digit number together with that name of that big group. So for example, this one is 482 million. There's the comma. 57,603. That's it. So if you notice, 482, 57, 603. Just 3-digit numbers. But I need to tack on the things and we're all set. Okay? If you wanted to write this gargantuan number, you would write it just like we said it. 482 million. I'm going to run out of room here, so I'm going to go to the next line, but I'm going to put a comma. 57,000, right? With the comma, 603. That's it. Now, you can really see why using the numbers is way better than the English, but you should know how to write these in English as well. Okay? All right. So let's go back to the integers. Now that we got the whole numbers under our belt, let's look at the integers as a whole. We've got the whole numbers together with their opposites. Now, I think it's important that we understand how these positives to the right of 0 and the negatives to the left of 0, how they get along. And the short answer is they don't. All right? If you take a number, like let's say 5, and its opposite, -5, they hate each other. They are going to fight. When you get them together, they hate each other. And just the same way as if you take -8 and its opposite, 8, they hate each other. In fact, if you add those together, any of those whole numbers together, any of those integers with its opposite, you know what happens? You get total annihilation, which is really just a dramatic way of saying nothing is going to be left. You're going to get 0. So for example, if you wanted to add 7 to its opposite, -7, you get 0. If you add -3,418 to its opposite, 3,418, you get 0. A number and its opposite added together, always total annihilation. It gets super interesting though if you add positives and negatives that aren't opposites. Look at this 9 plus -4. There's going to be a fight. They're still going to fight. Positives and negatives, they don't get along at all. But if you take a look at this, here's a cool way to represent this. I've got 9, positive 9. And if I represent them with 9 P's, P is for positive, and then 4 N's for the -4, there will be annihilation if we think of them going pairwise. Those guys annihilate each other, those guys annihilate each other, and those guys annihilate each other. So what do we have left when all the dust settles in this fight? Well, we've got 1, 2, 3, 4, 5, I count, 5 positives. So the answer is just 5. Looking okay? Those N's and P's can be really useful to model this adding of the integers. But wait, what if you had something like this? Negative 45 plus 38. We could do N's and P's, but nobody wants to write that many N's and P's. So maybe if we just think of this, maybe we don't just imagine the N's and P's, and we ask ourselves these two questions. If you added these together, who's going to be left standing when the dust settles? In other words, which group, the negatives or the positives, has more guys? Well, we've got 38 positives, and we have 48 negatives. So there's more negatives than there are positives. The negatives are going to win. So you know what? I'm going to put down that negative right away. The answer is going to be negative. How many negatives will be left? Well, we just have to figure out, well, what's going to be left out of those 45 after we annihilate 38 of them, after we take out or take away 38 negative. So what if we just did that subtraction? Notice there's no negative sign on the 45. I'm just talking about how many negatives are there. 45. I need to take away 38 of them. They're going to get annihilated. And that just gives me 7, right? 7 negatives. Good. Good. Negative 7. That's what we have left. All right? So the N's and P's are great, but when you get larger numbers, it's a little tough to do that. So we can do this sort of questioning. Which one has more guys? That'll tell you what the sign of the answer will be. And then to figure out how many, you just subtract. You subtract the numbers. All right? Beautiful. All right, that's how the integers work. And with that, we're now ready to go back to the real numbers. So remember, the real numbers are the integers, which we see right down there, and all the numbers in between in those little spaces. And it turns out there are many more numbers in between than there are integers themselves. All right, so that's really where the show is. So let's go inside and start to explore some of the numbers that are in between the integers. All right, and here's a good group to start with. Let's talk about the fractions. Right off the bat, this is so important, guys. I can't stress this enough. Fractions are numbers. Fractions are numbers, just like all the rest. Okay? I want you to think of them no differently than the other numbers you've seen, the whole numbers, the integers, etc. Fractions are numbers. Now, they're special numbers. They're the tiny numbers that help us describe parts of things, but they're numbers. All right? And let's talk about how you represent them. Maybe some visuals will help us understand these fractions. So let's say you've got 3 candy bars on the table, okay? And you want to sort of use them to show somebody. Let's represent the number 3/5. 3/5, okay? So you don't want to eat all 3 candy bars. You don't even want to eat 2. And in fact, you don't even want to eat 1. You're just not that hungry. You just want a part of that 1 candy bar. 3/5 is a number less than 1. So you know what? I'm going to get rid of these other 2 bars. We only need this 1. So 3/5. Fifths mean we're going to split that bar up into 5 equal pieces. Let me do that here. 1, 2, 3, 4, 5. That doesn't look too equal to me. How about you? Nah, not good enough. Oh man, I'm embarrassed on my first impression with you guys on my fraction divisions. It's hard. Do your best, and I'll try my best. 1, 2, 3, 4, 5. 5 equal pieces. 2, 3, 4, and 5. All right, that's looking better. Now, the numerator tells us we want 3 of those fifths. So what we do is we just shade in 3 of them. Man, I have not gotten any better at my coloring. There we go. So that's a good representation of the number 3/5. Okay? Now, let's say you wanted to represent the number 11/40 using bars. Well, that's fine. Now, I don't know about you. Again, I had trouble breaking it up into 5 equal pieces. Forget about 40. What are you, crazy? So I can't do those. And I don't think anybody could really do a good job doing 40 equal pieces. So let's not. Here's kind of a shortcut to that. We call it benchmarking. Benchmarking. And if you think about it, if we were to go through and divide that bar up in all those 40 pieces, the end of the bar would actually be where the 40th piece ends. So halfway, right there, that's where the 20th piece, the right edge of the 20th piece would be, right? Making sense? We're halfway through the bar, 20, and then 21, 22, 23, all the way up to 40. Now, I want to know where 11/40 is. Well, that means I need to keep subdividing. Let's try this half thing again. Those are important benchmarks. Half of 20 is 10, right there. And that tells me that 11/40 should be just to the right of the 10th. That's where the 11/40 would be. Okay, so we don't draw all the lines, just important marks that we call benchmarks. So let me color this in all the way up to that purple division as best we can. Done. So benchmarking to approximate it. Ooh, I've got one other thing to tell you about these fractions. There's a very special one that got a special name. Percent, 74%. Percent just means hundredth. So 74% is just simply 74 hundredths. So if we wanted to represent that, this is another perfect candidate for benchmarking, right? So let's do it. If we had the whole thing, all the lines drawn out, the 100th piece would end right there at the end. This is where the 50th, excuse my squiggly drawing there, the 50th line would be. Let's see, half of that, if I go this way, I'm kind of, half of 50, is 25. I'm kind of going the wrong way. I need to go bigger than 50. Well, this is where 25 little pieces would be. Then another 25 pieces, that puts us at 50. So if we did another 25 pieces, that puts us at 75, doesn't it? So that's great. That's right in the neighborhood of where we want to be. 74 hundredths would then be just to the left of 75, even closer than what I have there, but I just wanted to make sure you could see it. This is 74 hundredths. So let me color in all the way up to that green line, to 74 hundredths, or 74%. Okay, looking all right? Very nice, very nice. All right, tell you what, we should also be able to go backwards. I've been giving you a number and representing it with the bars. Let's go the other way. What do you think, what number approximately is that bar trying to represent? Well, what we need to do is we need to find a way to break this up to see how much is shaded there. So let's see. What if we took this thing, 2, 3, 4, 5. Does that look reasonable to you? Like those pieces kind of look reasonable? 1, 2, 3, 4, 5. I just picked that. I just picked those right out of the air. It would have been nicer if they had told me that maybe it was some amount of fifths. Then I'd have a little better, an easier shot. They didn't, so I just filled it in. Let's see. So that means we got 3 shaded fifths and 2 unshaded. So this is representing 3/5. All right. It's a little bit tougher to go backwards, and there are many, many answers that would be correct for that approximation, especially if they didn't tell us the denominator. Okay. Wait, the best part about fractions is you're going to use them all the time in the real world. Like, for example, here, if you've got a 1-gallon container and you want to fill it up with 5/7 gallons of water for something you're doing, then you should be able to do that. It's the same idea, isn't it? First of all, let's break this up into sevenths, 7 equal pieces. 1, 2, 3, 4, 5, 6, 7. Let me make sure I got enough. 1, 2, 3, 4, 5, 6, 7 equal pieces. Good. And how many do we shade in? How many do we pour in? 5 of them. Good. You guys got this. Here's the blue water. 1, 2, filling it up. 3, 4, and 5. Okay, there it is. In fact, that's the idea behind measuring cups, right? A measuring cup is something like this, and it has those marks on it, so you don't have to do this every time. But just in case the container doesn't have that, you should be able to at least eyeball a pretty good estimate of that fraction. All right. Here's a cool one. Let's say you're looking at a map, and you've got this 1-mile path from start to finish. And there's a bathroom listed on the map, and let's say you have to go. So you want to know exactly how far it is from the start. Should you go at the start, or can you wait till you get to the bathroom? So let's see. Let's see if we can figure out how far from the start is that bathroom marked on the map with that green tick mark. So let's see. Interesting here. What if we use this as one piece? And then here's another one of them, 2, and then that would make 3. Does that sound reasonable that to the bathroom, it looks like it's 1/3 of the path? So it looks like 1/3 right there. I'm just shading it in a little bit darker for you. That's 1/3 of a mile, 1/3 mile. That's what we got. That's what we've got to the bathroom. Looking okay? All right. Tell you what, let me just give you a few final notes on fractions. And guys, let me just pause for just a minute. I know I'm moving through this material very quickly. If it's too fast, don't worry. We're going to slow down eventually. And also, you have lots of time to talk about this and work on problems outside of the video. If it's moving fine, don't worry. Okay, we're going to get to new stuff very quickly. All right, but we want to make sure this foundational stuff is really, really solid. All right, I appreciate you hanging with me. So let me just give you a few more notes on fractions here. You want to sort of understand this all or nothing when it comes to fractions. So here's a problem that'll help us do that. Let's fill in the blanks. How many 1/18 equals 1? How many 1/18 does it take to equal 1? Think of the candy bar again. Split it up into 18 equal pieces. If you want to take the whole candy bar, yell it out. Come on, I can hear you. Good. 18 equal pieces. Means you got to take them all. 18. 18/18 is 1. And by the way, there's nothing special about 18ths. 7/7, 100 100ths, 100%. That always equals 1. All right, so with that, how many 18ths would be about 1? What could we put in that blank numerator? What do you think? Yell some suggestions out. Good, very nice. Who is that? Who is that? All right, I didn't see you back there. Nice, exactly right. We could use 17, like 17/18 would be a decent answer for that. We could also say something like 16. Okay, that's still pretty close to 1. But you know what? 17/18, that's a great answer. Nobody's going to argue with that. Let's go the other way. How many 18ths does it take to equal 0? Yeah, right, of course. If you don't want any candy bar, then you better take 0/18. Exactly right. So therefore, if we had to approximately get 0, how many 18ths should we take? If we want to get almost 0, well, how about 1? If we just took one little 18th, a little sliver of that candy bar. Sound reasonable? There you go. So it's just sort of the extremes, all right? All or nothing of the bar. All right, very nice. Here's another important concept. If you have a fraction of an object, you want to know what's left. So complements, we call this complements. So for example, if you eat 3/7 of a candy bar, how much of it do you have left? Well, here's a visual that might help. If you imagine that candy bar and you split it up into 7 equal pieces, you take 3 of them, how many does that leave left? Well, you can count them right up there. 1, 2, 3, 4 of them. Now, hopefully that visual made it totally clear, but you could also see it just from the numbers, correct? The 7 tells us we have 7 equal pieces. That's why we're talking sevenths. We only have 3 of them. So what's left? If I take away those 3 from 7, I have 4. Okay? All right. 1/2 turns out to be a really, really important reference point when it comes to fractions. It's probably the first fraction that people even think about. Okay? So it's really super important. For example, if you want to know if you have less than or greater than 1/2 when you have 23/42, well, really what it comes down to is understanding, well, what is 1/2 when you have 40 seconds? And the answer to that is you just divide 42 by 2. Divide it into two equal pieces. And half of 42 is 21, right? So 21/42 is equal to 1/2. You need to sort of know that, and then you can compare 23/42 to it. Well, 23/42 is clearly greater than 21/42. So 23/42 is greater than 1/2. Looking okay? Just figure out what 1/2 is with that particular denominator, those pieces. All right? Now, having just said that, let's talk about ordering sort of different kinds of numbers, bunches of numbers. Let's say you wanted to put the following numbers. I'm going to give you a bunch of numbers here. And let's put them in order from smallest to largest. Okay, we got 5 numbers there. Right off the bat, just scream out, top of your lungs. What's the smallest number in that group? Yes, good. 0. Except for 0, everything else is positive, right? So they're all to the right side of 0. They're all bigger than 0. Remember, on the number line, as you go off to the right, the numbers get bigger. And as you go to the left, the numbers get smaller. Which one is the biggest out of those 5? Nice. Good. 1. 0 is the smallest, 1 is the biggest, and those 3 fractions, you can see they're all less than 1. So how about this? I'm gonna draw a little number line here. Here's 0. Here's 1. And now all we need to do, let me take those off the board. Now we just need to order the other 3. They obviously live inside 0 and 1, so let's do it. Here is something I think that will be very helpful. I told you about 1/2, how important of a reference point that is. Well, 1/2 is right here. I know that's not in our list, but it's going to help us put the other 3 guys in the right spot. Okay? Take a look at this. 7/16. Based on what we just said in the previous note, is 7/16 less than 1/2 or greater than 1/2? So let's ask ourselves, what is 1/2 when you're talking 16ths? Well, 16 divided by 2 is 8. So 8/16 is 1/2. That means 7/16 is less than 1/2. It's going to live 7/16 over here somewhere. Okay? Actually, pretty close to 1/2, as a matter of fact. 5/8 and 5/9. I'm going to let you make sure that you are comfortable with this, but 5/8 and 5/9, they're both greater than a half. They're both bigger than 1/2. See if you can make sure that you can justify that to yourself. So what that means is 7/16 is going to live over here, probably like right here. And the other two numbers, they're both going to be over here. So when it comes to figuring out, well, all right, putting those in order, I know 7/16 is the second guy in line, right? 0, and then 7/16. And then let me go over 1/2, and then the other two guys will be there. So let me take 7/16 off. Look at the final two numbers, 5/8 and 5/9. Now, we have 5 of both of them, 5/8 and 5/9. So this is going to be really important. Even though it's tough, we can make the decision right now. It comes down to the fact that when you take a candy bar, if you split it into 8 pieces, let's say you're splitting it with 8 friends, compare it to if you took that same candy bar and split it amongst 9 friends. If there are more friends, then the pieces have to get smaller, right? So the more pieces there are, the smaller those pieces have to be. So that means that a 9th is smaller than 1/8. A 9th is smaller than an 1/8. So be careful. I know 9 is bigger than 8, but we're not talking 9 and 8. We're talking 9ths and 1/8. So since we have 5/9 and we're trying to compare it to 5/8, well, 5/9 is going to be smaller than 5/8, which means we can order them like that. 5/9 goes on the left and 5/8 goes on the right. So here's the listing. I just wanted to have that number line so I could show you the 1/2. But here's the order. We've got 0 first, then 7/16, then 5/9, and then 5/8, and lastly 1. There's our order from smallest to largest. Looking okay? Thank you guys so much for hanging tough during this intense review. We did a lot, but we've barely scratched the surface of the real numbers. When we come back in our next lesson, we'll go even deeper and then be on our way to studying the operations on the real numbers. Excellent work today. Take care, and I'll see you in the next video.